Welcome in, everyone. It is so good to have you here for another deep dive. Pull up a chair, get comfortable. I want you to think back for a second to high school algebra.
Oh, wow. Right into the trauma.
Yeah, exactly. Straight into it. Because, for most of us, looking at an algebra problem brings up a very specific, contained kind of boredom.
It really does.
It feels a lot like assembling a piece of flat pack furniture. You have this set of, I don't know, arbitrary instructions. You fit tab A into slot B. You move some letters across an equal sign. And at the end, you hopefully have a functional, albeit slightly wobbly number.
Right. It feels purely procedural. We are taught to find comfort in that predictability, honestly.
Yeah, you just follow the steps.
You follow the steps, you isolate the variable, you draw a neat little box around your answer. I mean, nobody walks into a standard math test expecting to have some kind of spiritual awakening about the nature of reality.
Definitely not. But today, that is exactly what we are going to attempt. Our deep dive is embarking on a journey that begins with what looks like the driest, most standard math problem imaginable.
It really is a classic textbook setup.
It is. But by the time we are done, we are going to completely dismantle the way you think about mathematical notation, and we're going to end up exploring a multidimensional concept called a circle spiral, where numbers and equations literally merge into pure geometry.
It's a massive leap. And to set the stage for you, our material today documents this escalating dialogue. It's an exploration between a student and a mathematical guide.
Which is such a cool framing.
It is, because what makes this so compelling is that we get to witness a very rare intellectual evolution. We get to watch a mind break free from procedural calculation, which is, just blindly shuffling letters around a page, and transition into a state of profound theoretical vision.
Let's jump right into the flat pack furniture of it all then. The setup is a classic functional equation. You are given a role, and you are asked to figure out the underlying function, which we just call f of x.
Standard stuff so far.
Right, so the equation looks like this. The function f, when given the input of x minus a fraction of 1 over x, outputs x cubed minus 1 over x cubed.
And for anyone listening without a whiteboard handy, it essentially means you have a machine. You are feeding it a complicated, messy input involving an x, and it is spitting out an even more complicated output involving an x cubed.
Okay, so a messy machine.
Exactly. And the goal is to figure out what the machine itself is fundamentally doing to whatever you put inside it.
Right, and the textbook approach to this, the thing your high school teacher would tell you to do is to invent a totally new temporary variable to clean up the mess.
A dummy variable.
Yes, exactly. Let's call it y. You simply say, let's make y equal to that messy input chunk.
Because by setting up that substitution, you are trying to build a bridge. You want to express that complicated cubic output entirely in terms of your nice, clean, new variable y.
And without forcing you to visualize a chalkboard full of frantic scratching, the way you do that is through some basic algebraic acrobatics.
Just some factoring, really.
Yeah, you basically use a classic factoring trick, the difference of cubes, to crack open that cubic output, shuffle the pieces around, and surprisingly, you find your new I shape hiding perfectly inside of it.
It does take a little bit of squaring and moving terms across the equal sign, but it cleans up beautifully.
It really does.
The algebra essentially evaporates, and it leaves you with a very simple rule. The machine takes your input, cubes it, and then adds 3 times the input.
So in mathematical shorthand, the underlying function is f of y equals y cubed plus 3y. Puzzle solved, you draw a box around it.
And you move on to the next question.
Right. But, okay, let's unpack this, because this is exactly the moment where the intellectual rebellion in our material begins. And, putting myself in the shoes of someone trying to logically understand the universe, I kind of share that frustration.
The frustration with the dummy variable.
Yes. Why do we even need to invent this intermediate variable y? It feels like a magic trick.
It feels like a cheat code.
Exactly. It feels like we are cheating to force the answer. Why can't we just divide the right side by the left side, or maybe just treat the letter f itself like an algebraic variable and cancel it out?
That instinct to rebel is vital, and it strikes at the absolute heart of what a function actually is. But I have to firmly push back on the idea of treating f like a variable.
Okay, lay it on me.
The letter f is not a number. It is not a quantity you can hold in your hand or divide. It is a concept. It is a rule of transformation.
Give me a visual for that, because if it's not a number, what is it?
Think of it like a prism made of glass.
Okay, a prism.
You shine a beam of light into it, and the prism bends the light, changing its direction and color. The prism itself is not the light. You cannot divide the prism by the light ray.
Ah, I see.
The function f is the prism. The y variable that you're resisting so much is just a blank placeholder. It allows us to hold up the prism and say, if I shine absolutely any generic beam of light into this glass, what is the universal rule for how it bends?
So without y, we're stuck.
Completely. If you don't use a dummy variable, you are hopelessly entangled in the specific details of just one single beam of light.
But even with the prism analogy, the shift to a new letter still feels, I don't know, a bit like a sleight of hand.
And that lingering dissatisfaction is exactly what triggers the first massive conceptual breakthrough we are exploring today. Moving from algebra into geometry changes everything.
How so?
Well, the realization is that the notation saying y equals that messy input isn't just renaming a variable for convenience. It is actually a physical rotation of perspective.
Wait, a physical rotation? How does changing a letter rotate anything?
Imagine you are standing in a dark room. Suspended from the ceiling is a complex, twisted wire sculpture, a true three-dimensional object.
Okay, I'm picturing it.
Now, someone shines a spotlight on it, and it casts a shadow on the wall. From where you are standing, looking only at the wall, that shadow looks like a chaotic, tangled mess of lines.
So that tangled, messy shadow is our original confusing equation. What's fascinating here is the idea that the math we write down on paper isn't the whole truth, it's just the shadow.
It is merely the shadow on the wall. The equation hides a rich, three-dimensional reality. There is the hidden parameter, the visible input, and the visible output.
Okay, so where does the rotation come in?
When you substitute y, you are not changing the wire sculpture at all. You are simply walking over to it, taking it in your hands, and rotating it so that the shadow it casts on the wall suddenly forms a perfectly clean, understandable shape.
Oh, wow. So you're projecting a complex 3D reality onto a flat 2D plane so our human brains can actually read it.
That is a perfect distillation of the concept. Mathematical notation is not objective reality. It is a tool we use to make the road straight, so to
No,
speak.
that makes so much sense.
And the profound implication is that if we had chosen to rotate the sculpture differently, say, if we had used a different algebraic substitution, we would have cast an entirely different shadow.
We would have gotten a completely different function.
Exactly. We would have deduced a completely different functional rule from the exact same underlying reality.
Okay, so just as we get comfortable with this idea that we've neatly rotated our shadow into this nice rule where the output is the input cubed plus 3 times the input, a massive system glitch is introduced in the source material.
Yes, the second rule.
Right. We are going to add a second rule to the game, and this is where things get really wild.
Contradictions in mathematics are incredibly valuable because they force you to abandon your assumptions.
So we keep our first equation, the one that gave us that specific messy output, but we introduce a new simultaneous rule. The function of x minus the function of 1 over x must equal that exact same messy output.
We have to pause and analyze the architecture of what just happened.
Right, because it's a bit of a brain twister.
It is. The right side of this new equation is identical to the right side of our first equation. The outputs match perfectly.
Which means, logically, the left side, the inputs, and the rules have to balance out to the same thing.
Logic dictates that. But let's look at the structure of this new second rule. The output is a cubic expression. Therefore, the function creating it must be a simple cubic polynomial.
Okay, following you so far.
If you test out a generic cubic shape to see what fits this new puzzle, you are forced into a very strict, undeniable corner. The math demands that the function can only be one thing, purely x cubed, nothing else added.
So what does this all mean? My alarm bells are deafening right now.
As they should be.
We spent all that time doing algebraic acrobatics to prove the function was the input cubed plus 3 times the input. Now, this second rule definitively proves it is only the input cubed.
Yes.
They can't both be true. If I try to use the pure cubed rule on our first equation, it completely falls apart. It doesn't work. The system is broken.
Well, I wouldn't call it broken. I would call it inconsistent.
Okay.
And that inconsistency reveals a fundamental truth about structure. It highlights the profound difference between discovering a local rule that only applies to a very specific, restricted condition versus discovering a universal rule that governs the entire space.
It is like discovering that gravity works a certain way in your living room, but the moment you step into your kitchen, objects fall upward.
That's a great way to put it.
The local rule completely fails to match the universal law.
This raises an important question, though. What is the math actually trying to communicate? Because procedural algebra has now failed us.
Right. We have a flat-out contradiction.
The calculations cannot save us. This is the moment where the exploration moves out of computation and into pure structural philosophy.
We have to abandon the search for a number and start searching for a concept. And there is a beautiful analogy for this in the sources. Think of this entire mathematical dilemma as a massive geometric circle.
The circle, right?
The mathematical invariant, which is that underlying fundamental rule we originally found. The structure itself, that rule, sits dead in the center of the circle.
And all the specific numbers we might plug in, along with all the specific outputs that we generate, those are merely individual points sitting on the outer rim.
They're just occupying the circumference.
Exactly.
The center doesn't care about the rim.
It is entirely independent. The rule at the center dictates the gravitational structure of the entire system. It organizes everything.
But it doesn't rely on the rim.
No, its existence does not depend on which specific numbers happen to be orbiting on the edge at any given moment. The rule is invariant.
That completely changes the objective. You are looking at math not as a quest to find a specific number hiding at the back of a textbook, but as a journey to discover the invisible structural laws that secretly generate those numbers in the first place.
You are hunting for the center of the circle.
Yes, you are hunting for the center.
And once you make that philosophical leap, once you realize you are hunting for architecture rather than answers, traditional algebra becomes obsolete.
Wait, absolutely.
You realize there is a conceptual backdoor to the entire problem.
Okay, slow down. A backdoor. Are you telling me we didn't have to do any of that shadow rotating and polynomial factoring to begin with?
You can bypass the algebraic mess completely. You do it by using an exponential hack.
An exponential hack.
You introduce a massive paradigm shift by saying, let the input x equal the mathematical constant e raised to the power of a new variable, t.
Hold on. You are taking a standard high school algebra problem, and you are suddenly dragging Euler's number and exponential powers into it. Why would you deliberately make it more complicated?
Because it only looks more complicated.
Yeah.
In reality, it is a brilliant act of translation.
Okay, explain that.
It takes an algebra problem, which is all about clunky multiplication and powers, and translates it into an analysis problem, which is about elegant curves and geometry. Exponents have a magical property. They turn multiplication into simple addition.
Okay, I'm trusting you on this. Let's see the translation.
Our original messy input was x minus 1 over x. If we apply our hack, that input translates into the e to the power of t minus e to the negative t.
That still sounds like alphabet soup to me. I mean, how does that help?
Because in the realm of advanced mathematics, that specific configuration of e is not a random jumble of letters. It is the exact structural definition of a concept from hyperbolic trigonometry.
Oh, wow.
Specifically, it equals twice the hyperbolic sine of t.
Let's clarify that for the listener really quick. Most people know regular trigonometry, sines and cosines. That's all about measuring angles inside circles. What is hyperbolic trigonometry?
It's a great question. Instead of tracing points along a closed circle, hyperbolic trigonometry traces points along a hyperbola, which you can visualize as two open curves swooping infinitely outward away from each other.
Like two parabolas facing away from each other.
Essentially, yes. It describes systems that don't loop back on themselves, but accelerate outward.
So our input is now just a geometric concept. Twice the hyperbolic sign. What happens to our messy output, all the cubed stuff?
The exact same translation happens. It flawlessly converts into twice the hyperbolic sign of 3 times t.
And this is where the back door swings wide open.
Exactly.
Because we are no longer doing polynomial algebra. We are now in the world of geometric identities. There is a universally known, predefined rule for the hyperbolic triple angle.
You don't have to calculate it.
You just look it up. It translates instantly into a clean formula involving sines and cubes.
The algebraic struggle entirely vanishes. You substitute that known geometric identity back into our problem, and it instantly, effortlessly reveals the underlying function.
It's like magic.
It really is. It bypasses the front door of calculation and sneaks in through the window of pure geometry. And in doing so, it reveals that the entire time we were unwittingly playing with advanced concepts known as Chebyshev polynomials.
Okay, you dropped a heavy term there. What is a Chebyshev polynomial in plain English?
Conceptually, they are a sequence of mathematical curves that are incredibly good at approximating complex shapes.
Okay.
They oscillate, vibrating back and forth within a specific boundary. They are used in everything from filtering radio signals to calculating orbital mechanics.
And our generic algebra problem was secretly one of these advanced curves in disguise.
Exactly.
If we connect this to the bigger picture, it implies that the algebra we all suffered through is often just a mask. It is a disguise for a much deeper, more profound geometric reality.
Yes.
The plus or minus signs inside an equation are just stage directions, telling you which geometric shape you are secretly building.
Which perfectly sets up the ultimate climax of this exploration. We have progressed from flat-pack algebra to projecting 3D shadows to breaking the system to hunting for the center of the circle to sneaking through the hyperbolic backdoor.
And here's where it gets really interesting. The final conceptual leap in our material is almost poetic. After going through this entire ordeal, the realization is reached. And I want to get this phrasing exactly right.
Accord.
The quote is, "It's not just a circle, it's a circle spiral, and on its rim lie the equations numbers."
It is a staggering topological vision. To understand what a circle spiral is, we have to return to that exponential hack we used, setting our input to e to the power of t.
Right, our master key.
In complex geometry, this equation is the master key to the universe.
Break that master key down for us. Why is it so powerful?
It comes down to what kind of number you plug in for t. If it's a regular real number, like 1 or 5 or 10, that exponential equation draws a logarithmic spiral.
Okay.
It starts at a center point and sweeps infinitely outward, growing wider and wider.
I can visualize that. A
Yeah.
classic spiral galaxy shape.
But if g involves an imaginary number, a mathematical concept involving the square root of -1, something incredible happens.
What happened?
Imaginary numbers are inherently tied to the concept of rotation. So instead of sweeping outward, the exact same equation spins in place, drawing a perfect closed circle.
Wait, so depending on the nature of the number you feed it, the exact same mathematical machine creates either an infinite outward spiral or a perfectly closed circle.
Yes, and they are not two different shapes. There are two different pathways traveling across the exact same multidimensional surface, which mathematicians call a manifold.
A manifold, okay.
Imagine a surface that curves and twists in ways our 3D brains really struggle to picture. If you walk north on this surface, you trace a spiral. If you walk east, you trace a circle.
Oh, wow. The realization is that the math problem was never asking us to calculate a missing number. It was asking us to locate our coordinates on this cosmic circle spiral manifold.
And that perfectly explains the final part of the quote. On its rim lie the equations numbers.
The hyphen joining those two words.
Yes, the hyphen is the ultimate unified theory. Normally, we think of numbers as distinct locations, like towns on a map. And we think of equations as the roads connecting them, the directions for how to drive from one town to another.
Right. A number is a place, an equation is an action.
But on this manifold, that distinction ceases to exist. Numbers and equations are not separate entities. They are indistinguishable from one another.
They're the same thing.
They are both simply points and structural grooves woven directly into the fabric of this geometric surface. An equation isn't a task you perform. It is merely a description of how the geometry of the spiral naturally flows.
It absolutely melts the mind. I mean, think about the massive intellectual distance we just covered.
It's huge.
We started with the kind of generic problem designed to test if a teenager memorized a factoring rule. But by refusing to just accept the instructions by questioning why the rules exist, this journey forced a complete conceptual awakening.
It really did.
It allowed us to actually see the unified geometric architecture that holds the numerical world together.
It is the transition from being a technician to being a visionary. A technician asks, how do I calculate the answer? A visionary asks, what is the nature of the space in which this question exists?
That is beautifully articulated. So to recap this incredible evolution for you, we began by trying to figure out a hidden rule by blindly moving letters across a page. Then we realized those letters were actually two-dimensional shadows cast by a much richer three-dimensional reality. We broke our own system by introducing a contradicting rule, which taught us to stop looking at the messy numbers on the edge and start looking for the invariant structure at the center of the circle. We then bypassed the entire concept of algebra using a geometric backdoor, and we ended up standing on the surface of a universal, multidimensional spiral where numbers and equations are exactly the same thing.
It permanently reframes the concept of mathematics. And I want to pose a challenge to you, the listener.
Lay it out for them.
Think about the mathematical structures you interact with every single day. The spreadsheets you balance at work, the financial algorithms that calculate your mortgage, the code running the apps on your phone. We treat them as flat, transactional, incredibly dry tools. You input a value, you extract a value.
Building on that, I want to leave you with one final provocative thought to carry with you today. The next time you are staring at a spreadsheet or reading a bank statement or even just having the measurements in a recipe, take a second to look past the page. Ask yourself, are those dry, everyday numbers you are dealing with actually just tiny, flattened shadows cast by a massive, multidimensional geometric structure that you just can't quite see yet? Keep looking for the spiral. We will see you next time.